Welcome back to the workshop. We want to continue taking a look at equivalence relations. So far, we've given the definition of what a relation is, and we want to continue looking at relations by giving some properties of relations. So let's take a look at those. So here in our definition, we have three properties that a relation can have. So let R be a relation on a set A. So three properties. The first one, if for each x in A, so R being a relation on a set A means that R is a subset of A cross A. I believe this is called the Cartesian product. A Cartesian product, A cross product. It's all the same thing. All right, so R is a subset of this. So if for each x in A, we have that x is related to itself. Okay, so every element that we can find in A, pull it out and say, is it related to itself? Yes or no? If yes, then R is called reflexive. All right, so that's our first property, the reflexive property. All right, so again, I want to make sure that it's clear. We're going to take a set A. So here's a set A. We go in and we find that point X. And based on whatever the relation is, right, does X comma X belong to the relation? Is X related to itself? If X comma X is in the relation, no matter what X we chose, for all of them, if X comma X, right, if 1 comma 1, 2 comma 2, purple comma purple, well, I don't know what the set A is, right? It might be colors, it might be people, it might be numbers, whatever the set A is, and whatever the relation is, if we can take any element from A and find that it's related to itself, then that relation is called reflexive. All right. So our next property, if y is related to x whenever we have that x is related to y is true. So if this is related to that, if y is related to x whenever x is related to y, if that is true, then R is called symmetric. So notice here we have the symmetry over R, right? If we know that x is related to y, okay, so we're given that. We know x is related to y. Okay, cool. It's symmetric if y is also always related to x, right? So if we start off with x related to y, x comma y. So whenever x is related to y, if we know that R is also related to x, then it's called symmetric. Okay. Let's see here. So that looks something like x comma y belongs to R tells us that y comma x belongs to R. Or whenever we have x comma y is, we can find that or show that y comma x is in the relation, then it's called symmetric. Excellent. Now, whenever we have that x is related to y and y is related to z, whenever we have this, and it follows that x is related to z, then R is called transitive. Okay, so what we're doing is we're skipping over the y and going to the z. If we can go from x to y, y to z, then we should be able to go directly from x to z. That's what we're looking at when we're talking about transitivity. Right, so the reflexive property, symmetric property, transitive property. A relation can be transitive, it can be symmetric, and it can be reflexive, it can be symmetric, and it can be transitive. Okay, so we'll talk about each of these properties. So let's look at two examples. So let's say we have a set S, 1, 2, 3, and a relation on S. We want to determine which of the three properties, reflexive, symmetric, and transitive, are satisfied by the relation defined on S. So let's look at each of at each of these. So for now, we're not worried about giving justifications, not so much anyway. We'll get into that just a little bit later. So, reflexive. So here I have a 1. Is 1 related to itself, right? Well, I suppose here I have a 1. For each x in A, our set A is actually labeled S here, and it's 1, 2, 3. Is 1 related to itself? Yes. Is 2 related to itself? Yes. Is 3 related to itself? Yes. So is it reflexive? Yes, because every element in the set is related to itself. Excellent. So what about symmetric? All right. So we see that 2 is related to 1. And if it's symmetric, then we should be able to swap the order and find that 1 is related to 2. So is 1, 2 also included in this list or in this set? Yeah, it is, right? 2 is related to 1, 1 is related to 2. Excellent. So let's just continue working on. Of course, 1 being related to 1, you can swap that without any problems. So we just need to make sure that we can do that for every element, so or for every ordered pair. So 2, 1, do we have 1, 2? Yes. 2, 3, do we have 3, 2? Oh, no, we don't. So it's not symmetric. And just to be clear, it's not symmetric since we have that 2 is related to 3, but 3 is not related to 2. And that's good notation here. To say two things are not related, we can simply write the R with the line through it. And that's good notation for saying not related. So if it were symmetric and we know that 2 is related to 3, then we would also know that 3 is related to 2. But in this case, we don't have that 3 is related to 2, so we don't have that symmetric. All right, let's see, the last one is transitive. And in this case, we can actually use our observation here that we don't have 3, 2. That will help us or become important here. So we can go from 1 to 1, and then we can go from 1 to 2. Can we go from 1 to 2? Yes, it's right there. We can go from 1 to 1, and then 1 to 3. Can we go from 1 to 3? Yes. So anything that has the 1, 1, 2, 2, 3, 3, that's trivial, because once I pair that with something else, it doesn't change what's happening. So the interesting thing is to consider these guys. So I can go from 2 to 1, and then 1 to 2. Is 2 related to 2? Yep, we found that over here. I can go from 2 to 1, and then 1 to 3. So I should be able to skip over the 1 and go from 2 to 3. Yep, that's right here, 2, 3. And I can go from 1 to 2, and then 2 to 3. Can I go from 1 to 3? Yep, still good. Let's see here. Then 3 to 1, and 1 to 3, of course, that's 3, 3. And 3 to 1, and then 1 to 2. Can I jump over the 1 and go from 3 to 2? No. So it takes a while. It can take a very long time to check all of these possible combinations, right? But it should yield some results. An extensive search says, yes, it works. Or in our case, we find that 3 is related to 1, and 1 is related to 2, but we cannot skip over the 1. But 3 is not related to 2. So I wasn't using the fact that it's not symmetric to show that it's not transitive, but I was simply observing that this same element does not belong to the relation R. Okay, 3 is not related to 2. All right, so 3 is related to 1, 1 is related to 2, but 3 is not related to 2. What does that tell us? It is, this is not transitive. All right, so the relation R is not transitive. Excellent. So let's take a look at one more example. Let's have G be the set of all graduates of CUAA. Okay, so anyone that's graduated from Concordia University, Ann Arbor, is in our set G. No matter what the name of the university was, right? Before it was a university, it was just Concordia College. And then before that, it had a different name, I believe. A long time ago, they only offered 2-year degrees. So when they bumped it up to 4-year degrees, it became Concordia College. Anyway, so let's let G be anyone who's graduated from here at Concordia. Let's say that X is related to Y, means that X attended CUAA the same year as Y. So 2 people are related if they attended school at the same time. Okay. So determine which of the 3 properties, reflexive, symmetric, and transitive, are satisfied by the relation. So reflexive. The question here is any person related to themselves? Or, in the context of the problem, the question is, did any person who graduated from CUAA attend school the same time as themselves? Of course, yes, whenever they were in school, that is when they were in school. So yes, it is symmetric, or it is reflexive. Yes. Because each student attended the same time as himself. All right, now symmetric. Now in this case, let's say 2 people are related. Let's see here, Tom is related to Jerry. Okay, Tom went to school at the same time as Jerry. Excellent. Now the question is did Jerry go to school the same time as Tom? Right, because order can matter in a relationship, and so we have to confirm that it doesn't matter. And the relation that's described, attending school at the same time, that thing does not have an order. So it essentially removes the order from the relation, and we say, yes, it's symmetric. I can put that in whatever order I want. Tom is related to Jerry because Tom and Jerry went to school at the same time. Jerry's related to Tom because Tom and Jerry went to school at the same time. No big deal. So is it symmetric? Yes. Excellent. And then transitive. Is it transitive? All right, so this one, you might initially think yes, but we can come up with an example that shows that it's not. And so let's do that to show that it is not transitive. So I'm going to say no with an exclamation point. No, it is not transitive. All right, so let's consider this. Consider student A who attended let's see here. Let's say they attended from 2010 to 2014. Okay. Student B who attended, let's see, a little bit after, but still overlap of time, 2012 to 2016. And student C who attended, let's say 2015 to 2019. Excellent. So we can see that student A and B attended at the same time in the years 2012 and 2014. Kind of looks like a 1 there, 2014. All right, so we have that student A is related to student B because they both attended in 2012, 2013. And we have that student B is related to student C because they both attended in 2015, 2016. Let's see here. But there's no overlap between students A and C. Student A graduated in 2014, and student C did not even begin until the next year. Okay, so A is related to B, and B is related to C, but A is not related to C. So R is not transitive. All right. So that's all that we wanted to take a look at for those initial examples of these three properties. We'll continue taking a look at more examples of these three properties in our next video. So I'll see you guys back here in the workshop in just a moment.